Uh, Good morning, everyone in China, and maybe good evening to those overseas. We are very happy to be here. Today we have invited Professor Haitao Li to give us a talk. Let me give a brief introduction about Professor Li. Professor Li is chair of the supply chain and analytics department and the founding director of the Lab Advanced Supply Chain Analytics at both at University of Missouri, Louis, in the United States. And he holds his PhD degree in operations management from University of Mississippi. Dr. Li is his research interests focus on optimization modeling, algorithm design, and their applications in the broad domain of supply chains, including supply chain network design, supply chain configuration, resource allocation, project scheduling, and vehicle routing. Professor Lee serves as associate editor of the Journal of the Operational Research Society and Transportation Journal. And he is also editor board member of the International Journal of Project Management. And Professor Lee will give us a talk on data-driven optimization for modern urban logistics and transportation, from models, algorithms to applications. Let's welcome Professor Lee to give us his talk and share his thoughts. Please, Professor Lee.
Thank you, Professor Yuchuan, for the nice introduction, and also thanks Urban Lifeline for the invitation. It's really my pleasure to share with you this line of research I have been working on for multiple years, data-driven optimization. But today we're going to focus on the domain of urban logistics and transportation. I will share with you roughly three related subtopics on modeling, algorithm, and most interestingly, application. So, um, let's see. All right, this is where I am. Uh, so I'm located in St. Louis, Missouri. For some of you know a little bit about the geography. This is the Midwest of United States. Okay, as you can see, we are here at almost the center of US. Yeah, that's where St. Louis is. And there are several things you need to know about St. Louis if you don't, right? This is the arch representing the gateway to the West. Okay, so St. Louis does have a very rich history, and some of you uh, may like the sports called baseball. Okay, yeah. So St. Louis has a very good baseball team called Cardinals. I think many of us like beers, and this is St. Louis is the headquarter of Budweiser. By way, yeah. All right. Okay, before we get into the topic, I want to give you some idea about my research lab. Okay, yeah, Lab of Advanced Supply Chain Analytics at UMSL. So here, we have a group of my colleagues and students, PhD students and master students. We're working on primarily using advanced analytics and lots of optimization, to address all kinds of quite diverse range of applications across multiple industry. I just want to highlight a few here, right? Yeah, manufacturing, food and agriculture is a big stream. We're right now working on healthcare, construction, and certainly logistics and transportation. So here I'm also would like to mention, a number of sponsors of my research over multiple years. Some of the major research projects that's ongoing right now include the one funded by U.S. Department of Transportation and also U.S. National Science Foundation. Yeah. All right. So I'm going to start with some motivation. Okay. Yeah. I'll share my ideas about some, current challenges and opportunities in modern urban logistics and transportation. And then we'll dive into what do we mean by data-driven optimization, uh, modeling framework and methods. I do have several concrete application examples prepared I want to share with you, and I'll talk briefly about some research opportunities. And um, I'm hoping, we can have some good amount of time, right, at the end for questions and some discussion. Yeah, that would be great. All right. So challenges. We're no short of challenges when you think about logistics and transportation in an urban setting, right? Congestion, right? The picture on top, causing lots of delay. Especially the peak hours. The one on my left bottom corner, the uh, the huge problem of uh, climate contamination, right? The environmental impact of, carbon emissions through transportation, all kinds of transportation modes, remains to be a problem, right? And then often, we see all kinds of natural disasters, including, tsunamis, earthquakes, tornadoes happening. And sometimes they, impact our urban area, right? Yeah, with concentrated population. The last one I'm showing here is last mile delivery. This is one application I think China has been really leading the world, okay, doing really well. But there are still lots of challenges there, right? Yeah, how do you make sure, the right commodities, right, goods delivered at the right time, in the right place, to the right people, right, efficiently, yeah. So at the right cost. Okay, so certainly opportunities, right? Yeah, they often come together. Okay, yeah, there are lots of nowadays use of drones. Again, I certainly have been seeing, there are lots of innovative application of drones use cases that's happening in China. Okay, yeah, in the past, I would say 5, 6 years. I think US is really catching up. We're a little bit slower here. We often have some regulatory issues, to be addressed, but certainly, we're getting there. The one here we're showing, this is actually a very exciting way of growing, crops, okay, in agriculture. It's called controlled environment agriculture, or simply indoor farming. Um, so this really fits really well in an urban setting because here we're talking about using internal space, right? Yeah, indoor farming or vertical farming, using these frames where, you can have multiple layers to grow crops indoor. Okay, really exciting. This is one project I've been working on for multiple years, and I do want to share with you more. Okay, yeah, as one of the application example. Blockchain, right? Yeah, many of us, are perhaps even working on that, right? Yeah, I'm certainly getting more into blockchain. Very promising. There are some use cases, but I think it's still emerging. Okay, yeah, this is area is still new, and lots of opportunities there. So let me give you an overview, right? Yeah, when we talk about decision making, because that's really my my passion, okay? Yeah, my focus is to address decision problems, right? That often require the use of optimization. So this is an overview. To me, supply chain is perhaps um, the most the best arena for, all kinds of decision support methods, right? If not the best, right? Certainly one of the best arena. You, we often see all kinds of, decision problems in supply chain, in uh, at different levels. Okay, yeah. So, for example, strategic level, we could design a supply chain logistic network, right? We could talk about capacity planning. At tactical level, we could talk about, transportation, production planning, along with inventory control. Okay, or at very operational level, we certainly address lots of resource allocation, vehicle routing, sometimes mingled with scheduling problem. Okay, yeah. So what is what is the overall overarching research stream, right? Yeah. Whether we're talking about you know, a transportation logistic system or part of the supply chain system, right? I'm really seeing nowadays we should certainly simultaneously consider these multiple performance metrics. Okay, efficiency remains important. We certainly want to address safety, okay, in transportation. Yeah, sometimes quality of goods, equity, okay, there are some special population or certain area that needs, special attention. Resilience, right? We talk about this a lot, okay? Especially when the system is subject to lots of uncertainty and risk. Okay, yeah, and certainly sustainability, right? On the environmental side, certainly on the social side, and also economic side. Okay, yeah. So as you can see, these metrics are often conflicting with each other, right? The challenge and opportunity is really how do you achieve safety, right, or resilience while at the same time being efficient, right? In terms of cost or or lead time. Okay, yeah, this is a very big theme. Okay, yeah, and now let's talk about analytics. Okay, yeah, so forget about those jargons, different methodology, right? I want to start with the user's perspective. What do we use analytics for? People usually start with descriptive, okay? Yeah, to describe what happened using descriptive stats and data visualization. And then we go a step further to do prediction, okay? Here again, we can use all kinds of statistical regression, for example, methods or econometrics, right? And certainly the modern machine learning methods, simulation that can really do a good job on predictive purpose, okay, for predictive needs. On top of everything, and everything boils down to what? Making decision, right? Yeah, this is where we call prescriptive analytics, or where we need to use the methodology of optimization, right, to prescribe or recommend to people what to do and how to react. Okay, yeah, so very exciting. So you see these circles overlap. They overlap for a good reason. Okay, not just to you know to look nice, right? Yeah, so they overlap because some of the real world application require these different methods to work together. Okay, yeah, for example, the synergy between descriptive and optimization and predictive analytics and optimization. Okay, yeah, there are certainly opportunities there. So optimization, right? Yeah, very high level. Usually we build a model. The model will take inputs, okay, and data on this side. We have an objective to achieve, whether it is maximizing profitability or minimizing cost. And we often have, some technical requirements and business rules to be satisfied. The model will take all these input in and come up with recommendation or decision, okay, support, right? Yeah, for the decision maker. Yeah. So here is a very concise map of optimization. Okay, we can dive into this. I'll keep our discussion on this slides at high level. Okay, yeah, in the interest of time. So I classify optimization into two uh, large sub areas. One is deterministic optimization on the left-hand side and optimization on the uncertainty. Okay, yeah. So deterministic optimization, we can go further, right? Mathematical programming is certainly the most used. Okay, yeah, so powerful. And under it, you have all kinds of math programming model, right? Together with constraint programming and a lot of different types of heuristics, right? And under heuristics, we can differentiate special purpose heuristics that's often problem dependent or meta heuristics, right? Yeah. So I'm not getting into diving into meta heuristics where you can, you know, branch further, right? Like genetic algorithm, taboo search, and so forth. Certainly on the right-hand side, very important, right? How about decision needs on the uncertainty? Well, we can use stochastic programming, for example. Simulation optimization is very powerful, or robust optimization, right? Yeah. Um, Certainly at the highest level, most complex one is the so-called MDP, okay? Yeah, Markov decision process. So many of us are intrigued nowadays, and some of us are probably working with AI, right? So let me use what we described earlier, right? I'll put these methods in this map, kind of the two-dimensional coordinate system, to show how we map this. Okay, yeah, in this coordinate system, right? So in the horizontal axis, we're focusing on predictive and purpose. And vertical axis represents prescriptive use. Okay, so you can see many of the optimization methods are on the top, right? Because they serve, prescriptive needs. Many of the AI methods, right, colored in yellow, they are they are kind of to the right, right, to the right, because they are most of them are used for predictive purpose. So you see some methods are in this area like approximate dynamic programming, simulation optimization. So those methods are often can address or will utilize methods for both predictive and optimal and prescriptive purpose. Okay, I hope this map gives you a good idea on, the purpose, right? The need of using these different techniques in optimization and AI. Okay, all right. So let's talk about data-driven decision support, right? Often, we may have lots of data, right? Nowadays, data is really availability is not a problem anymore. Often we have the so-called big data, in large volume, velocity, speed, right? And variety that's available. Then at the center, is our optimization tool, okay? Our model and methods. We take these inputs, we recommend decision that often will impact either, the infrastructure or resource allocation or some sort of business operation. And you see these arrows, go back and forth, right? Yeah, because, often um, we can do this as a feedback loop, right? Yeah, depending on what's observed in reality, we may revise our model, certainly revise the data, right, to do this in a continuous fashion or iterative fashion. All right, so let's get into a little bit math. Okay, yeah, I keep my um, introduction, in this talk at very high level. Okay, so our formulation will all at the generic level. So this is a way to represent a generic optimization model, right? Or mathematical programming model. So X here represents a vector of decision variable. A and B are coefficients, okay, are constants in the objective function and constraints respectively. So we have objective function G, right, which is a function of decision variable X and A, and the parameter A, and we want to maximize or minimize. F is the constraints, okay? So depending on the nature of the functional form of F and G, mathematical programming can be classified into linear programming, integer programming, nonlinear programming, or mixed integer programming. Okay, it's a very rich research area, but very, very useful, in a variety of domains. Okay, business, engineering, certainly transportation and logistics. All right, so we probably heard of the term data driven, right? It's like, again, a buzzword, very often. But exactly what does data driven optimization mean, okay? Or data driven decision support mean? That's the focus of this talk, okay? I'm going to summarize data driven optimization approach into different paradigms, okay? So these paradigms are summarized in terms of complexity, okay? And the easiness of implementation, okay, from easy to more complex one, okay. So paradigm one, it's the basic use of prescriptive optimization, very fundamental, very easy to use. And then I'll talk about integrated simulation and optimization, okay, that get us further into how we're going to address uncertainty, right? A little bit more complexity. A very useful approach, which is called two-stage stochastic programming. Okay, yeah, we'll certainly talk about that. And finally, um, this so-called MDP or stochastic dynamic programming, which is very powerful in terms of its modeling capability, but also computationally challenging. Okay, yeah, we'll talk more about that. So paradigm one is pretty straightforward. Okay, essentially, in this case, data-driven simply means, we can always input different set of data into our optimization model, and the model will prescribe the corresponding optimized solution. Okay, that's corresponds to the current input, right? Yeah, so very straightforward. In this case, the model can often remain the same, right? But the data can always change. Okay, yeah. Once you change the data, you will get a different optimal solution, right? And often in this case, as many of us know, you can do sensitivity analysis, right? Yeah. Or what if analysis, to examine the effect of changing parameters, okay, on the optimal solution. So well, this is very easy to do, but one significant drawback is this approach does not consider uncertainty, okay? Yeah, because we are relying on the so-called point estimates or the mean or average of these input parameters, okay, without addressing uncertainty or risk explicitly. All right. So yeah, then, in reality, right, many of our applications involve uncertainty. So this is why I want to share with you this well-developed, well-known simulation optimization approach. Okay. Yeah. In this case, you see, this is where I highlight the use of descriptive and predictive analytics because we're going to need these techniques, right, to come up with the probability distribution of our uncertain parameters, right? You see, this is where, that overlap comes into play, right? Remember the three circles and they overlap? Yeah, to get the probability distribution first, right, we need some descriptive or some predictive methods. And then it's this, this diagram on top is this integrated simulation optimization approach. Okay, so um, we don't have time to explain meta heuristics, but essentially this is a high level solution strategy to search the solution space of an NP hard, often combinatorial solution space, right? Yeah, so this is optimization based on local search, right? In local search, we search the neighbor of the current solution. But since now we have uncertainty, we use optimization, right? Sorry, we use simulation, mostly Monte Carlo simulation, right? With the probability distribution we got to estimate, to evaluate each candidate solution or neighborhood solution. Okay, so this works iteratively, yeah, and it's the idea is very simple, but practically it's very useful. Okay, yeah, it's very useful. So I do want to share this very, uh, again, another very useful modeling approach called two-stage stochastic programming model approach with recourse. Okay, this is a method that has been developed for decades. This is a very structured way to, model uncertainty, okay, inside an optimization problem. Now, it is important to understand two-stage here has a very important meaning. Okay, yeah. So this type of model applies for the decision problems where you have a clear, distinctive two-stage feature. Okay, let me explain what that means. So there is this first stage decision we call here and now. Okay, it's like I need to make a decision right now. Think about a farmer. Okay, yeah, think about a farmer who needs to decide what crops to grow. He needs to make the decision right now, but of course the yield of the crops is uncertain, right? Because of the weather, rainfall, sunshine, right? And then there are some decisions, right, that the farmer can make later. Okay, in the second stage, this is called recourse decision, second stage decision. Okay, so in our notation we use x to represent first stage, here and now, also kind of proactive, right, decision, and y omega, right? Substrate omega represent the second stage or reactive or recourse decision. That's associated with each scenario, right? Omega here represents a scenario, um, representing those, random parameters or uncertainty. Okay, yeah. So this is the high level um, description of the model formulation. Basically, the objective is to optimize both the cost of the first stage decision and expected cost of the second stage decision. Okay, yeah, it's the whole system, right? And the constraints include those involve only the first stage decision variable x and those involve the second recourse decision y omega that's defined for every random scenario. Okay, omega. Yeah. So in this case, this is a very structured way to model this class of problem where you have this two-stage structure, right? Yeah, very powerful, very useful. Okay, widely applied. But then you may ask, oh, well, why two-stage, right? Yeah, I think that's a very good question. I asked that exactly the same question when I first, you know, get get into stochastic programming. Often, our decision problem are in will involve multiple steps, right? Multi steps. Um, this brings more dynamics into the problem. Okay, this is where we need to use, I mean, not need to, right? I would say a very useful approach, right? Very powerful approach is this so-called Markov decision process. Okay, the MDP approach will allow us to model a very complex dynamic system, dynamic stochastic system that also involve decision. Okay, yeah. So basically, MDP, to me, you can understand MDP as a Markov chain, which is a stochastic process, right? But where people need to make decision. Okay, yeah. So on top of the Markov chain, if one needs to make decision, that's kind of, you have a Markov decision process. So again, this is a well-developed approach, very powerful in terms of modeling. You can model, the state transition, right? Yeah. S here represents state of the system, which is a function of the current state, the decisions made, that's xt, right? And also some exogenous information. So a very important concept here is the concept of policy. Okay, yeah, pi, right? Often here the solution goes beyond just a specific numbers, right? It is more like a decision rule. Okay, we call it policy. Yeah, this approach is very flexible because it can allow us to make sequential, dynamic, and adaptive decision. But at the same time, it's also very computationally challenging. Okay, yeah. So some of you know the Bellman equation, right? For solving dynamic programming, but in practice, Bellman equation, quickly become intractable. Okay, yeah, because of the dimension of the problem. Yeah, so this is more of an illustration of how MDP works, right? You see the decisions are made sequentially, right? So at the initial stage, right, make a decision, and then we observe new information comes in, right? We're gonna update the system make another decision. This is the idea of dynamic and adaptive. Okay, yeah. So so this is where we need to talk about algorithm. Okay, yeah. So for this very challenging problem, MDP model, how are we gonna solve it? Okay, there turns out there are some good solution strategy that try to approximate the Bellman equation. Okay, yeah, approximate the Bellman equation rather than attempting to solve it exactly. Okay, yeah, we call it approximate dynamic programming. I don't think we have time to dive into the details. Okay, but just to let you know, the all these different types of ADP, approximate dynamic programming, will rely on three techniques. Okay, here in each row, that is value function approximation scheme. How do you approximate the value function or cost to go, right? It's gonna mostly use forward iteration using simulation. Okay, and also again, I want to emphasize the use of deterministic optimization methods because often we need efficient deterministic methods to solve many subproblems, okay, inside an ADP algorithm. Okay, yeah. So here I give you some interesting view of what type of optimization models, okay, that could be involved when we address um, uh, urban logistic and transportation application. Okay, yeah. So let's start with the centralized decision problem, right? Yeah, application. So here I divide application from two perspectives, that is between deterministic and stochastic, static and dynamic. Okay, yeah. So let's put different application there, right? Transportation network design, right? Very static, right? Because it's strategic decision that's not made very frequently, right? Well, transportation planning going to be more dynamic, right? Yeah. And routing and scheduling, right? Very dynamic, very frequent, right? And disaster relief, that may involve uncertainty. Okay, so you can see resource allocation distribution move a little bit to the top, right? And we call it decision theoretic because here we consider only one decision maker, right? But everything we talk about here almost has some application where there could be multiple decision makers. Okay, yeah. So this is where the game comes into play. Okay, we call it game theoretic. For example, when you do network design, there could be competing companies, right? Competing decision makers who are making network design decision competitively, right? In transportation logistics, often there is the issue and motivation of coordination, where we need to consider different decision makers' decision simultaneously, and they often interact, right? Transportation and traffic planning, right? Yeah. So this is another example where you need to consider the game interaction of different decision maker, but in a very dynamic and uncertain environment. So in terms of complexity, yeah, this is this is what I believe. Okay, yeah, you see the red bar, right? The darker the color, the more complex. Okay, if you agree, yeah. So pretty much we move from the left to right, right? It's more complex, right? And from what deterministic to stochastic, right? From bottom to up, it's more complex. Okay, yeah. I hope that you find it interesting, kind of high level view. All right. So I do have a few concrete examples. Okay, yeah, many these are all my current ongoing research projects. Okay, yeah, I will share with you first my work on distributed manufacturing system design. Okay, yeah, that's funded by USDOT. So here we um, focus on the so-called distributed manufacturing, right? So which is very different from the traditional manufacturing paradigm, right? Where you people emphasize economy of scales, right? So you build very large, facility, and that's not large enough. Let's build industry clusters, right? We call industry clusters, right? To increase the scale. And often you have a centralized company, right, that plan for everything. But in distributed manufacturing, it's very different. Okay, so here we're talking about a lot of small scale facilities, but they are distributed. Okay, they are smaller scale and they can make their own autonomous decision. That's where the game come into play, right? And but often, there could be also a centralized parent firm, right? Like we are showing here. We have a centralized firm who still want to coordinate, right? So you still have this centralized firm who wants to coordinate everybody, yet these three different distributed facilities all have their autonomous decision-making process. And interestingly, their objective function can be different, right? Yeah, that can be really interesting. So what we're showing here is illustration, right? Let's say, there is only um, limited available raw materials available from the parent company, right? But three distributed facilities each have their own, objective. Okay, yeah, to do their production planning, and they're gonna compete for what? For the limited raw materials. So how do you plan for that, right? In this setting, yeah. So we came up with what we call centralized autonomous coordinate system that we allow each facility to make their own decision, right? Yet we support the parent firm, okay, to do some sort of coordination to coordinate their decision to achieve some global corporate level metrics. Okay, yeah. And we got some very encouraging preliminary results. Okay, yeah, through our procedure, we can achieve better corporate level performance, right? Um, comparing to the traditional approach where everybody just compete, right? And it turns out, the resource can be allocated also more efficiently. Okay, yeah. And what is also important here is in this case, we actually also can achieve better objective locally, okay? Because the coordinate scheme does consider each distributed facility's own objective, okay? Yeah, take that into consideration. Yeah. The second example I want to showcase is this very interesting work. I'm very excited about vertical farming, right? As we showed earlier, or control environment agriculture. I work with my colleagues, Dr. Purcell and Miss Alice Roach. Both of them are from agribusiness field. Okay, so this is also an excellent example of interdisciplinary research, right? And and why this is relevant to urban logistics and transportation, right? Think about its advantage. Okay, there are lots of well-known advantages of vertical farming, right? Especially for urban farming because it presumably will shorten the transportation distance significantly. Okay, if we can grow right crops, fresh vegetables, in the urban setting, right? Yeah, so that's great. And the yield is very high. Okay, usually it's 3 to 4 times higher than the conventional agriculture method, and the availability of crops is year round, right? So you can eat, you know, some fresh vegetable even in the winter time, right? That's not possible in conventional agriculture because everything we're talking about here is indoor, right? It's in a controlled environment. So there is no seasonality anymore. Okay, you can have uh, fresh vegetables, on demand, year round. Sounds great, right? But you know what? What turns out is happening is, there are so many indoor farming startups, at least in the US. Okay, I think China has some, and maybe some companies in China in this area are doing great. But we know here in the US, many startups fail. Okay, people, companies put money, lots of investment, but many startups of indoor farming fail, especially as they are trying to grow, okay, are trying to scale. Yeah. So that's a big research question to us, right? And we approach this this question from the supply chain perspective, okay? The operational side, right? So we really look into the decisions on, where to build, right? Where to build indoor farming facility, how many, and what is their size, right? Their configuration. And most importantly, the crop portfolio. What crops to grow and how much? And how do we factor all these economic factors like cost, capacity, and variable cost, fixed costs into consideration, okay, into our economic study? Yeah, that's very unique approach. And we build an optimization model, to optimize these decisions. Okay, yeah, facility location, facility configuration in terms of capacity and choice of different growing methodology, right? Yeah. So for example, Dutch bucket, nutrient film technique, and deep water, all these are indoor farming, indoor agriculture techniques, right? Yeah. And again, crop portfolio. I call it crop portfolio. Okay. What crops to grow and how much, okay, which is not trivial at all. And most importantly, how to distribute, right? How do you serve the local markets, right? Yeah, you see, this is really a gap, okay? I mean, there are lots of research in agricultural science, right? Precision agriculture, right? The so-called precision agriculture, but they just purely focus on the growing side, right? The production side. So we really goes beyond production side to bring into the picture of distribution and transportation and operation. Okay, yeah. All right. So we did a case study in the St. Louis area. Very interesting study. We talked to some local farms and subject matter experts to collect some real data for our use case. We did a base case scenario, and you can see, I think this number is, I cannot say this is 100% a reality, okay? But I can definitely say at least 90%, okay? This is very close to what you will see in a, kind of a indoor farming startup. It barely make even, okay? As you can see, it barely make even. You lose a little bit, right? This is not that bad. But we also did, using sensitivity analysis, right? We can answer these what if, right? What if we can reduce the fixed cost and variable labor costs, right? As you can see, if you go this way, right, the cost is reduced and the profitability goes up, right? That's very encouraging news, right? Which is also not surprising. I think this one is really interesting, right? If you can raise the price, right? Because the vegetables are fresh and often high quality. So often you have a price advantage. So your price goes up, profitability goes up. That's great. But the problem is, as you can see, when you take into account of the demand price relationship, right? So there is not an unlimited uh, range, you can increase your price unlimited, right? Because when you raise your price at certain level, people will switch, okay? So you will actually lose your demand and profit goes down, okay? I think this is a really interesting finding and provide the startup a tool, right, to do this kind of analysis, okay? Yeah. So another interesting finding is this, demand, right? We talk about the challenge of scale. When they try to scale, they often lose money. Yeah, look, this is what we're showing here. Okay, we explain why. Because when you try to increase serving, more demand, right, more market share, you need that expansion, right, in your capacity, which is costly. Okay, this is why you see the profit actually goes down a lot. And as you are able to do this, over time, right? Yeah, you can further grow your production and market share. You are improving, but still, right? You may not even break even. So what's the solution, right? The what we also find is if if we can simultaneously use advanced growing technology, so this curve can potentially be moved up. Okay, it's very possible, with that, the indoor farming company can make a reasonable profit. Okay, yeah. So this just shows you the importance of using advanced analytics and optimization. Okay, yeah. So we don't have much time. I will go through the last one relatively quickly. Yeah, but this one is a project I did a longer time ago. Okay, yeah, it's actually 10 years ago, more than 10 years ago, but I'm still working on it. Okay, we had a recently a paper published, on this topic. This is about scheduling large scale projects under both resource constraints and uncertainty. Okay, we call it stochastic RCPSP, or resource constraint project scheduling. This is where remember we talk about Markov decision process. Okay, you have a very large, very complex dynamic scheduling problem, which is very complex, right? Itself by itself already, where we have uncertainty. Okay, so in this case, the duration of each task or activity is uncertain. Well, you still have this limited resource. Um, that gives you a very challenging problem. Okay, yeah. Don't think we have time to go through this small example, but let me quickly jump to uh, the application, right? Yeah, so this class of problem has lots of application in urban logistics and transportation. For example, multimodal transportation, right? Often there you need to schedule, the routes, right? With limited availability of buses or trains, sometimes bicycles or drones, okay? Often it's a mixture of routing and scheduling problem, right? Yeah. Also last mile delivery, right? Yeah, where you want to schedule the activity, the task, while, also addressing some sort of uncertainty, right? Yeah, the travel time, for example. Yeah. Logistic disaster relief. Yeah, certainly another potential application. So this problem is a sequential decision problem. Okay, that's the approach we use. Okay, um, so the challenge here is really the solution methods. Okay, yeah, we develop a very novel approximate dynamic programming approach to integrate simulation optimization and reinforcement learning. Okay, in machine learning. Yeah. So let me show you the framework. Okay, yeah. Quickly jump to the framework. So this is the most recent paper we published on this topic, where we formally present integrated simulation, optimization, reinforcement learning. Okay, so this is where we use reinforcement learning to train some samples. Okay, to estimate a decision state pair, and then also use simulation and optimization to evaluate, each candidate solution. Okay, so this is a nice way to combine, uh, these multiple different techniques to solve this very challenging MDP model, and also large scale. Okay, yeah. So I have all these references listed at the end. So if you are interested, feel free to get the paper and take a look. So our algorithm performs very well. Okay, we compare with, you know, all these available, benchmark solutions. The last column is our algorithm. So you can see they are they are really state of the art and outperforms, the existing benchmark solutions in many different instances. All right, I'll wrap up very quickly. Okay. Um, I think application is very exciting. Okay, yeah, and I encourage everybody to go to the real world. Okay, yeah, talk to industrial practitioners, right? To come up with this so-called use-inspired research. Really exciting to me. Often the innovation starts with the problem. Okay, and I think on either modeling or solution algorithm side, there are lots of room to make innovation. Okay, yeah, on the technical side, yeah. The question is, how do we, first of all, build an innovative model, right, for a real world impactful problem? And then, if the model is very challenging, how do we design and implement an algorithm to solve it efficiently? Okay, so this is a list of references. Uh, that's it. Yeah. Thank you. I went a little bit over time, but
Okay, very good. Thank you so much, Professor Lee.
Sure.
uh, our audience, do you have any questions? Just feel free to turn on your microphone and speak out. Professor Lee, I believe many of our audience have the background in civil engineering or transportation engineering. So could you please give them some suggestion to first is how to relate the data-driven optimization
Yeah,
to the civil engineering and transportation engineering applications. I saw you mentioned some transportational examples, but could you please expand more? And the second is if the students don't have much background, uh, could you please give them some idea how to start to learn this field?
absolutely. Absolutely. Let me address the first one first, okay? Um, let me share a more concrete example on multimodal transportation. Uh, one stream of research that we are also working on right now is the use of drones, right? Remember the picture using unmanned aerial vehicle. And I know this has lots of traction in China as well, lots of success. So this is a great example. So the application, I have been working on is to use drones to deliver medical supply. Okay, that include, for example, vaccines. We had a paper published in Transportation Science about 2, 3 years ago. Okay, of using drones to deliver vaccines to less developed country. Okay, less developed region. Yeah. So what is important there is um, that we cannot use drone by itself, right? The drone has to be utilized with other transportation modes. Okay, for example, roads. In our earlier paper, we consider boat. Okay, yeah, we did a case study in a country called Vanuatu. Yeah, um, so it's a small country in the South Pacific Ocean. Okay, they actually use boat, indeed, and walking. Okay, yeah. So this is where you have this problem, which is very real, right? That needs optimization. Okay, and the model is somewhat non-trivial, right? Because you need to coordinate you know, um, different use of transportation modes in terms of spatial, right? Spatial characteristics, where to use which, right? And sometimes we may address more even detailed routing decision, right? Yeah, in transportation, routing, right? How to deliver, those customers. Yeah, so there are lots of application, and then I think of disaster relief. I think this is a huge area, very, very important. This is where it involves, decisions at different level, right? So first, we could address more strategic, resource positioning, right? Where do you build storage, right? To position those materials or medical or food in need, right? Ahead of time. You see that idea of proactive, right? We talk about proactive. This is before a disaster, right? We call it proactive. But then how about emergency response, right? After a disaster happens, how do you distribute, right? How do you evacuate, right? I mean, they are just, unlimited, okay? Really exciting. So, so this is why I really encourage you, everybody here and your team, right? I think the first one is my main message. Okay, yeah, go to the real world. Okay, go to the real world. Industrial engineers, right? Transportation engineers, civil engineers, and if you are civil engineering, I encourage you to think about the synergy between industrial engineering, right? Between operations research, right? Because there are lots of synergy. I actually works with my colleague. Many of you know Zhiqiang, right? Yeah, Zhiqiang Chen, my friend and colleague at UMKC, which is my sister campus. So we actually had some really exciting discussion about how we can work together, right? Because he um, brings the decision needs, the challenges in civil engineering. For example, bridge assessment and maintenance, right? You need to dispatch inspector, right, to examine all these bridges. How do you make that efficient, right? And yeah, I mean, we can approach that as a some sort of a routing and scheduling problem, right? You see, so there are lots of I would say interdisciplinary synergies, opportunities. I think going to the real world is very important. And this use inspire research to me is really valuable. Yeah, I would certainly encourage you to find right real world relevant optimization problem. Okay. Yeah. So optimization is great. Yeah. That be okay? First question, right? Yeah.
Yes.
Okay. Now
Our
for the
audience, anyone have
yeah,
question?
anybody? Yes. Any other questions? So Yuchuan asked the second question about young researchers, right? Or someone
Right.
who are early in their career, who wants to get into optimization. I want to share with you this book I wrote 3-4 years ago, and it was published in 2023. This is a very systematic coverage on optimization modeling. Okay, yeah. So I introduce this different modeling techniques in the bigger umbrella of supply chain. Definitely, you can find topics related to transportation and logistics. You know, the the fundamental value and motivation of this book was to really fill the gap on modeling. Okay, see, nowadays we have some very powerful software available. Okay, we can take advantage like Groby, right? Cplex. Some of you may be already using it, but to use those solver and software, researchers, we need to build the model. Okay, yeah. So the ability of building a model and being able to communicate the model formulation, in a rigorous way is a very important skill, and it's often a gap. Yeah. Any other questions? Any comments, questions?
Professor Lee, let me ask you one more question. Because today
Sure.
everyone is talking about AI, and
Yeah,
can you share your thoughts about how to bring AI into this field, or what's the current status of the application of AI in the optimization modeling for supply chain?
that's a great question. Before I try to answer that, Yuchuan, I want to clarify. By AI, are you talking about the different techniques in AI, or are you talking about the generative AI like ChatGPT or DeepSeek?
Maybe the second one.
The second one, right? You see?
Yeah.
Yeah, that's interesting. Okay, good. Okay, so um, I'm I use generative AI. In my case, I use ChatGPT, right? ChatGPT occasionally. I'm relatively on the more conservative side. Okay, I'm not very proactively promote the use of generative AI for optimization modeling because I do not think model yeah, I do not think generative AI right now is capable to build a customized model based on the formulation. Okay, I don't think it's there yet. I think generative AI can often give you a a model formulation for a standard problem. Okay, let's say if you ask it to do, show me the model formulation of a generalized assignment problem, right? Yeah, most of the time it will give you fine. But modeling is still, I think, a skill that needs lots of expertise because often it needs communication between the modeler, the researcher, and the subject matter experts, right? That conversation. So that's number one. I think perhaps the most useful part, Yuchuan, I can think of is perhaps on coding, uh, on computer programming, okay, coding. Let's say you have a optimization model already built, which is challenging, and you are considering using to design some algorithm. Okay, let's say genetic algorithm or taboo search. I think in this case, you can get some very good help, some support from using those generative AI that gives you maybe some example code, right? Yeah, some starting point that you can start with. Okay. And actually, one of my colleagues here at AMSO, she teaches our, PhD level, PhD seminar in optimization, where she actually has encouraged the students, she used ChatGPT, encouraged the student to use ChatGPT to come up with some general code for some algorithm like simulated annealing or taboo search, which works pretty well. But uh, I have to I I have to say the researchers still need to go through it because it's not 100% trustable. Okay, it always make errors. The errors are almost always expected. So it doesn't mean we just use it just to copy paste. It should not be used like that. Okay, we use it as a tool. Okay, it's like a search engine, right? Like we use any search engine, Baidu, Google. Now we have this generative AI tool, which I think it's useful if we use it in the right way. Okay, yeah, properly. Yeah.
Thank you, Professor Li. Since it's light time over there where Professor Li lives, so maybe we have to end our seminar now. So welcome, thank you for everyone to participate in this Urban Lifeline public seminar again, and look forward to your future participation and involvement. And appreciate Professor Li's time and his sharing of his expertise. And let's just stop here. Thank you, everyone. Have a good night or have a good day.
Thank you. Thank you all.
Okay, bye-bye, Professor Li.
Bye. Thanks.